Swayam Prabha. Digital India. Educated India.
Welcome you all to the next class. As you notice that I have completed the main part of the syllabus as well as the highlights in the last few classes. So, in this class we will start with the tutorials covering over. Not only this class, maybe next 2, 3, 4 classes we will try to cover the tutorial parts. So, that it will help students a lot how to read, what to look for, how to understand the subject when they read from my slides and they read from my lectures. So, therefore, this is a kind of thing. So, initially I have given very simple ones, then I have taken to a little bit more tougher side. So, you can see the level that it grows from simple to the to a somewhat serious kind of things too. Okay, look at this particular slide. I have asked very simple things in this, just a kind of a warm up kind of an exercise. Expand the following: EXAFS. So, what is EXAFS? I am sure you all know: extended X-ray absorption, fine structure, spectroscopy, and expansion of MALDI. Okay, I am sure you know that. Matrix assisted laser desorption ionization. CV, it is used for cyclic voltammetry, ESIMS, electrospray ionization mass spectrometry. So, there are a variety of these things. This is just few I have given for as an example. This does not mean only these are the ones. So, you should familiarize yourself with some of the important cases, this kind of short form usage. Also, you need to know primarily what are the kinds of side chains are present in the amino acids, particularly those which are important in the bioinorganic chemistry. What do you mean by important in the bioinorganic chemistry? Those which extend coordination to the metal center. So, which are those things? We have already looked at during the lectures: aspartic acid, glutamic acid, histidine, lysine, serine, etc. So, all of these have got the side chains which are very important. You can easily see these things from my notes, and you can fake out the aspartic is the one where you have the carboxylic, histidine is the one where you have the imidazole, etc., etc. I have also given you the pKa's, and you know that the alcoholic OH will have very high pKa, while the COOH will have very low pKa, and imidazole and the phenolic will have in between, and the SH will have slightly higher too. So, this is another question, that is, arrange these amino acids, that aspartic, histidine, lysine and serine as per the increasing order of their pKa. How will one know this? If you know the side chains. So, how will you know the side chains? You need to familiarize yourself. So, if you familiarize yourself with the side chains, at least about 10 amino acids, half a dozen definitely, and about 10 amino acids. If you can be familiarize yourself with that, it will be very nice. Okay, go to the next query. So, this is something to do with the essential trace elements. I gave how much they are present for a body weight of particular thing, etc., etc. So, based on that, these are all essential trace and ultra trace elements: iron, copper, iron, cobalt, copper, iodine, etc., etc. So, this you can easily make out. These are all present in the human tissue. Iron will be the highest among all these things, followed by copper, and then followed by iron, followed by cobalt. So, these are the kinds of things you can look at the actual values. You do not need to worry about what I say in this particular tutorial. This is just to warm you up with the kind of questions that would come later on. So, I repeat that you need to read all these things in the perspective of this. So, now you got a feel some things what to be read. Let us get some more idea from this another one. It is again very simple warm up thing. So, I have designed some queries for simple things like to say true or false. The natural ionophores which function in the biological systems are only macrocycles. Is it only macrocycles? No. There are macrocycles a lot, there are non-microcycles also. Okay, so you have both macrocycles and non-macrocycles, therefore the statement is not correct. So, in a metalloenzyme, the immediate vicinity of the transition metal ion can be considered as a coordination complex. That is how I started with from the beginning. So, you look at the metal center in any metalloprotein, it is connected to the side chains of several amino acids, one or more amino acids, sometimes even a heme followed by amino acids, and I told you that. So, therefore, this can be considered as a coordination complex. So, what is the answer? You understand now, I told you already that. Okay, coordination complexes can generally be used in disease diagnosis and therapy. Yes, absolutely. I have given initially in the introductory case itself a couple of slides on which I have listed the elements, their compounds, and in what kind of a diseases they are found, all of these. So, I am not going to repeat all of these. So, you can see that you can study all of them. So, therefore, yes kind of thing. So, uptake of ions and electrons through food by the biological systems is often challenged by the antagonism and synergism. Yes, absolutely. We know that a lot of elements, entry of one of the element is opposed by another, entry of one of the element is supported by other, opposed by other is called antagonism, supposed by the other is called the synergism. So, therefore, we have all the antagonistic, synergistic, all these things is so true statement. The next query is the protein synthesis. I am giving more elaborate answer than required true false. True false is for you to write, but this is where I am giving reasoning. So, therefore, kindly listen carefully when you are listening to this particular part of the lectures, make note of the things too. So, protein synthesized at the ribosomal RNA can act as enzyme only when these undergo chemical and structural transformations. Absolutely correct. Reason why? The reason is when it is made at the ribosomal RNA, so it just connects one amino acid with the next one amino, the next etc., forms a chain. So, may not have enough sufficient time to completely structurally fold. So, there may be a partial folding. Unless a complete folding is occurring, you do not expect a function to happen. You cannot expect. That is what I told you. A protein, an amino acid joining together polypeptide into a protein by the kind of a three-dimensional structure. Once you have the structure well folded, then you will have a function, then it is an enzyme. I explained to you several times that. Okay, the oxidation state and spin state of ion cannot be unambiguously be determined by mass biology. No, that is not correct. It can be very unambiguously determined, because this is only the technique where you can measure both, identify both oxidation state and spin state of the iron. Okay, there is some on the exercise on the hard, soft, acid base. As you know, this is dependent on the if you have a species, then you have to identify which atom would be binding, etc., etc. First thing, then that atom, whether its oxidation state or formal kind of oxidation state, size, parameters you need to think in the mind before you can make whether it is a hard or soft. Then before you can make acid and base, then you need to make whether it has it can donate electrons, then it will be base. If it has some empty orbitals, can accept electrons, then it will be acid. So, therefore, Lewis acid, Lewis base, hard and soft. I think you can sit at home and do all this, because I have given all the things. For example, carbon monoxide, maximum number of cases it is through the carbon. So, therefore, that you need to take. Okay. So, therefore, carbon whatever you know the things. Okay, I have given another thing to just warm up that between the techniques and the phenomena that you understand, the phenomena you observe are given here. So, the phenomena you can establish is given on the list A, and the technique is given on the on B, and sometimes you can have more than one also. So, establish primary coordination sphere. So, you can establish by EXAFS. Of course, you can also establish by single crystal XRD. Okay? And primarily these are the two where you can fully identify the things in that. See, this is establish primary coordination sphere in a metal or protein. Establish the presence of copper 2 plus and the number of histidines. Establish the presence of the copper 2 plus and the number. So, presence of the copper 2 plus, suppose you take a apoprotein, you add a copper 2 plus, you can look at even absorption spectroscopy, absolutely no problem. And you can also look at the EPR spectroscopy to find the find that particular copper is there, etc. Absorption you can use, EPR you can use also. Of course, single crystal XRD and all can be used for all. So, therefore, let us not take that as a common thing in these, and if you want you can use that as one of the answer too. And the number of histidines can be formed from EPR. How? You have a super hyperfine coupling, then you have first thing is spin the nuclear spin. So, the electron spin coupled with the nuclear spin. So, nuclear spin is 3 over 2, therefore 2 into 3 over 2 by plus 1, that will be 4 lines, and each of the 4 line can be further to Ni plus 1. I is the nuclear spin for example nitrogen present for the histidine. So, from that you can make out how many lines you can calculate and get it. So I hope you understand that. Everything can be formed from single crystal XRD. Okay, established protein proton coupled electron transfer process by metal enzymes. Proton coupled electron transfer you can find primarily and by the voltammetry. So, electrochemistry or voltammetry kind of thing, no other thing will give all. You can do to some extent NMR etc., but you have to do huge amount of titrations, but it is not a direct method. Direct method is electrochemistry. So, establish the presence of a metal ion in iron proteins, in the iron proteins. Okay. Establish the presence of an ion, Moss-Bayer. So, if you have a Moss-Bayer here, yes, absolutely you can find straight away. Of course, you can also use EPR etc., and you can also use for that matter some stage the absorption, but mainly of these kind of things. Okay, I also explained to you at some stage that the octahedral field splitting is being the T2G to EG level splitting can be reduced or increased by the type of the ligands that you have, by the nature of the metal ion you have, the oxidation state in the metal ion you have. For example, if you take a particular metal same and then use halides and oxygen ligands, nitrogen ligands, carbon ligands is already given to you. Halides will be splitting less than the oxygen, oxo ligands, less than nitrogen, less than carbon ligand. So, how do you explain this? So, this is not by the electronegativity, it is by the pi acid character, not the sigma part of it. It is the pi aspect of it, not the sigma aspect of it. All of the ligands will bind to the metal center through sigma. So, the sigma bond characteristics are not so important, but the pi bond characteristics, whether the pi base, pi acid. So, this is called pi acceptor, pi donor kind of things. That is where you can see. So, with this kind of a warm up, I will take you into a bit of involved type, somewhat a little bit more involved. Okay, a few of them would be easier, but some of them would require you to think. You can only think after you understand my lecture, and that is how it is. Okay, let us see this some of the. Let's see what the question I have here for you. What do you think that the biological inorganic chemistry will deal with? How do you describe the metal ion center present in a metal enzyme and why? So, what do you think that a bioorganic chemistry will deal with? Bioorganic chemistry deals with the role, interaction, triggering aspects of activations and triggering aspects of inorganic elements on the biological systems. Most relevant one is the protein or enzyme. So, that is what one would expect. In fact, that is what all we have covered also. And also you can see that not only the enzymes, proteins, you can also have nucleic acids can also be there, other biological molecules. To extend this, you can also say their interaction with the cells, their interaction with the organs as well. These are all one can expect in this. So, already I have answered the second part of this question, how do you describe the metal ion center present in this in the metal enzyme Y? I have already explained to you that it is can be considered as a coordination complex, because the metal ion is bound to the side chains of the metal or protein. Side chains will form a small coordination complex, and now it is a coordination metal ion, primary coordinations and the secondary and other aspects of the protein enzyme. Protein. So, therefore, a metal a coordination sphere of a metal center influenced by a protein, that is what. Okay. And this is the reasons are that there is an influence by the primary coordination, there is also influence by the secondary coordinations and other things too. Okay, let us look at another query, not so difficult one, but somewhat easier. So, why do you think that about 15 to 20 elements together forming 0.1 weight percent of the total body composition would be important? So, what is the reason? So, there are some 15 to 20 elements which are the together is present in less than point, together, not each one is 0.1 weight percent, together is so very small quantities, because these are present in the enzymes, their total quantity will be not so high, but important because without these enzymes the body will not function. So, therefore, even though they are very small, the total 15-20 elements together is only 0.1%, but still they are very vital, because they make the entire enzymes to work, cell signals to function, all these kinds of things, or the biochemical processes go on in the body. So, all of these are triggered or initiated or processed or favored or supported by the metal ions in metalloproteins, metal ions, anions, various kinds of things. Okay, so let us come to the third one. Given the example that the iron 3 plus taken in water in test tube versus the iron 3 plus taken in protein medium, how do you compare these two to give biological inorganic chemistry perspective? This is something which you need to think a bit. I would say this is a bit of involved. Probably for that matter, even the previous question also a kind of an involved one. So, all that I am saying is you take an iron 3 salt, put in the test tube, leave in the water, within a short period you will find the small precipitate, then over a period of time this will become insoluble kind of a precipitate. As you know very well, the iron 3 plus get hydrolyzed initially to hydroxide and later on to oxides, where the iron ions are bridged by the oxo species etc. are non-reactive. Okay, if you take the same thing and put the iron 3 plus into a protein or an enzyme, no, it will not allow the iron to get hydroxy, iron to get iron oxide etc. No, and the enzyme will or protein will bind to the iron center, so that its hydrolysis part, its hydrolyzing capabilities are reduced. Unless you have a few coordinations open, even then you will not find Fe2O3 etc., you will find some other kind of reactions in that too. So, therefore, the biological inorganic chemistry is grown when the iron is put in a protein, but the same iron 3 plus is put in water, it dies off as Fe3O4. Going via other oxides, hydroxide, oxide, Fe3O4 finally as the dead end, and this is absolutely the beginning, and this will be flourishing the whole thing etc. Okay, so I hope you understand this is how you need to really think and address. So, what are the amino acids capable of binding to metal ions in metal enzymes? How and why? Partly I answered in the previous questions, some things like aspartic, glutamic, serine, the arginine, then you have cysteine, then histidine, then tyrosine and tryptophan. Some of these things can bind. So, therefore, you sit and see. I have also given in one of the slide a list of these amino acids which are involved in the primary coordination sphere, and a few of them may be involved in the secondary coordination sphere of there. Those which are involved in the primary coordination sphere can also be involved in the secondary coordination sphere too. So, these are all kinds of things so these are all reason is the kind of a side chain that you have, and the side chain can bind to the metal center. Let us look at this particular query you have here. While the side chains of the amino acid residues present in proteins can bind, why the nature has used units like porphyrin? How the porphyrins will help in metal enzymes? This requires a much more comprehension. This you can understand and explain only when you have gone through my lectures to good extent. The first part is okay, yes, there are metal enzymes, metalloproteins, and are they not happy? They are all from the side chains. Why the nature has chosen porphyrins? What could be the thing? The porphyrins, they will provide a different kind of a stability, different kind of a redox character to the metal center. Therefore, in some cases the nature has chosen the porphyrin like molecules. In other cases it has chosen just the side chains. In third category, both porphyrin as well as the side chains, all of these are there, and modified side chains also. So, there are a variety of these things. So, all of these to control, regulate the reactivity at the metal center, particularly its redox properties. You can say in the black box catalytic properties. Instead, you can say the electron transfer properties too. So, therefore, that is how these will help. I have already answered. Okay, let us look at a bit more. This is the previous one just now I completed, and the porphyrins, their role is obviously an involved kind of a query. Let us look at another one. Can the same given ion, for example copper 2 plus, show different function in biological systems? If so, how does it do? If not, what are the problems to exhibit different functions? What are the problems in order to exhibit the different functions? So, see that. So, same ion can be involved in variety. If you take iron, there are several hundreds of enzymes are there, and at least a dozen classes of enzymes are there. If you take zinc, there are several hundreds of enzymes are there, at least more than half a dozen classes of enzymes are there. Take copper, there are several hundreds of enzymes are there, a dozen different classes of enzymes are there. So, therefore, same ion can show different functions in biological systems, provided the protein is different, provided the protein mantle and the immediate surrounding, the primary coordination, the secondary coordination, and the whole protein is different. So, therefore, in such cases this can be this is possible. Okay. So, if you think it will not do that, then there is no meaning of the extending half a dozen proteins, half a dozen enzymes for the same metal ion, nothing of that kind would be there. Okay. So, go to the next one is a list 10 different functions that the metal enzymes generally show. This is a routine question, you can just look at my slides like electron transfer, proton transfer, oxidative reactions, reductive reactions, group transfer reactions, hydrolysis kind of reactions, and ligase kind of reactions where you break the bond without using the water, break the bond with using the water, hydrolase, and you can use ligase, you can use lyase, all those kinds of things, variety kind of things are there. You can always make the things there. So, that is all possible that you can straight away get from my slides, and this is not an involved one, this is just to try to make yourself familiarize. That is the reason why I gave. So, you can warm up yourself with all those things. Now, how do you establish whether a given amino acid residue present in the metal enzyme is critical for its function or not? How will you establish anything is critical or not? So, when somebody claims something is critical, you bring absence of that, you make an absence of that, you remove that one. If you remove that one, that is not there. If that is not there, if the function is still there, that means that is not required, that is not essential. On the other hand, you remove the thing, and if when you remove the function is not happening, then that is obviously required. So, similarly in this as well. So, what you do in a metal enzyme, a metal ion is there and an amino acid is bound to that. Now, your query is that whether that amino acid is really essential for the function or not. So, what you need to do? You have to replace that amino acid by something else. This is what is called the mutagenesis. I have already talked to you site targeted mutagenesis. You can have one site, you can have multiple sites, these are all known very well. So, using the site targeted mutagenesis, you can replace that particular amino acid by not by in the protein in its genetic version, and then express, then you get a protein in the protein in which that particular amino acid is not present, and some other amino acid which does not have the same side chain is present. Therefore, and at that stage you check the function of the enzyme. If you check the function of the enzyme and if your answer is the function is stopped or function is changed, then you say yes, that was required. Same thing is true even if I ask a question, instead of one amino acid in a metal enzyme of iron, I will replace the iron by some other ion. How do I know that the iron is essential for that particular? So, I just remove, I put some reagent like the EDTA or some other chelating agent by which I can take out the metal ion from the protein and make apoprotein and see whether the apoprotein gives any function or not. From that you can establish. Okay, come to the next question in the involved type. The pKa of imidazole is shifted from 7 to 4.6, 4.0, 3.8 respectively in presence of cobalt 2 plus, nickel 2 plus and copper 2 plus ions respectively. So, what all you understand from this? So, what do you understand from this? In the water you have the pKa, the 7.0 brings down. So, that means these for example, the imidazole group is activated by these metal ions. They try to displace the proton. The imidazole has got NH. Now, the metal ion competes for this NH. So, it will become N and the metal ion, NH to N metal ion. Okay. So, and in the process it brings down the pKa from 7 to 4.6. So, let us take as 5. So, 2 units difference, that means about 100 fold kind of thing. 7 to 4 is 3, 10 power 3, 7 to 3.8 roughly. So, that is the kind of thing for cobalt, nickel, copper, this. The smaller the pKa that brings, that is the stronger that it will bind also. So, all these things are important. So, that is why the side chain pKas are modified in presence of the metal ion, and metal ion will displace the proton and then bind to itself, and thereby coordination sphere is formed. Okay, some more examples of involved tutorials. Okay, what all you think that it can happen when the original transition metal ion is replaced by another transition metal ion in a metal enzyme, and why? I have already answered this question previously when the amino acid has come. Okay. So, now you take let us say a copper zinc enzyme and remove the zinc, put copper. What will happen? Check the activity. Okay. So, the activity may be stopped, it may show a different kind of activity or less activity. There are 3 possibilities. The activity is reduced, no activity, or altogether new activity. There are 3 possibilities in this. So, therefore, you can easily make out whether that is. So, what happens, etc., everything. In this process, if you are a researcher, you should be excited that you take some metalloprotein from natural source, remove the metal ion, put a new one and start playing with it to get a new enzymatic activity. That is how your research will go, and you can publish all the results for the future and for the future utility of the same. Okay? And that is how it goes. You can use for some bulk preparation of certain molecules, materials by using such kind of things too. Okay, as you know that while iron 2 plus and cobalt 2 plus, for example, are labile, the iron 3 plus or the cobalt 3 plus is inert. What makes it so and why is it so? So, I am sure I have given you the plot, I have given you different ions and their the labilities, inertness, etc. As you know, the lability can be identified from the crystal field stabilization energy of the ground term minus the crystal field stabilization energy of the activated complex. If this were to be positive, it is a labile; if this were to be negative, it is inert kind of thing. And also it depends upon the spin state and the size of the ion, all of these. In alkali it is only size of the ion, in main group elements it is only the size of the ion, but in transition metal ions both the size as well as the spin states, all of these will be playing a role. Okay, let us look at another question. An ion protein is given to you. By choosing only one spectroscopy instrument, only one spectral instrument, not more, how will you establish whether the ion is in the given in the given protein is +2 or +3, whether it is in the low spin or high spin, unambiguously. I have already answered in the earlier question in a different form of the question. Which spectroscopy instrument will you choose, and how will you establish both the oxidation state and spin state of the ion in that particular protein? Okay. So, this is I am sure I have already answered to you earlier. It is a mass bias spectroscopy, and the mass bias spectroscopy based on the isomer shift and quadrupolar coupling. So, you can easily find out, you can look back into the things of that type. Okay. In a metalloprotein, you were told that the metal ion is bound to histidine 51 and glutamic 55, but you are asked to prove this. You are given a wet biochemical, biological and microbiology based lab. What is your strategy? How will you prove this? If you answer this, I am sure you will be able to design some research problems for yourself or for your supervisor. Okay. That is where the thing is. Answers are there in the question. Earlier I used to, when I give histidine glutamic, I do not used to give the number, now a given number, that means the position, histidine 51, glutamic 55. Now you know in the protein, in that 51 there is a histidine and the 55 and there is a glutamic, okay, bound to this. So therefore one can do, so you are asked to prove this particular thing in that. So you can do by wet chemical methods and biological methods. So biochemical, biological, where you can replace this particular amino acid by a different one and show the property that it does not show, it is required by this. Similarly, for a glutamic you change the thing by genetically or even chemically. So, some of these can also be converted chemically, the histidine chemically, the glutamic, and then look at the function, and then you can try to prove that. So, these are the kinds of strategies. For this, what you require? Wet lab. You require the biochemical, biological kind of things that you require. That is why in the question I have given that. Okay, you are given a metalloprotein and an absorption spectrophotometer and a wet chemistry lab. What all can you obtain by using all these and how? Okay. So, if you are given a metalloprotein, you can remove the metal ion, you can add the metal ion, you can add different levels, you can study absorption spectrum. Now, you can also remove that metal ion, keep adding the other metal ions and look at the change in the absorption spectroscopy, or even as a function of concentration, even function of pH, then you can establish whether they are binding, they are not binding. If they are binding in an octahedral center, they are binding into tetrahedral center. All of these information can be obtained from these. Okay. Okay. So, we will continue in the next class further with several more questions of this kind, which is some of them could be involved. Some of them could be simple, some of them could be very involved. Now you understand, you have to apply your mind and think in these ones. Thank you very much.